So I'd like to welcome all of you to this Parametrize and Arrhythmia seminar. And in the spirit of what we try to do, we really don't limit ourselves to the work that is directly arrhythmias or directly cardiac arrhythmias. This field really is much broader than that, and you all know that there's a lot of interdisciplinary, cross-disciplinary, and overlaps. And one of the objectives that I've had with the seminar series is really to broaden the horizon of everybody and try to see where overlaps exist and where we can work at the overlaps between different fields. And this is a good example where ion channels are proteins, and proteins move, and they have dynamics, and they have properties to the structure that affect their function. And in fact, in my laboratory, we've done a lot of modeling of ion channel function, and now we're starting to relate function to structure at the molecular level that Dave will talk about. So we're happy and lucky to have David Sept wrote this seminar in this institution and in this department. He's one of my biomedical engineering colleagues. And Dave has appointments in several departments and received his Ph.D. and I think he's an undergraduate from the University of Alberta in physics. He then continued to do a postdoctoral fellowship for a number of years at UCSB, where he focused on what you'll hear today, or the field in general of what you'll hear today. And I think that the important thing to get out of this lecture is that there are major possibilities of collaborations and interactions between different groups here, and also with different approaches to investigate what we call cardiac bioelectricity and so
I think Jordan contacted me in probably late summer or something to give this talk, and I initially said, "Oh yeah, sure, sounds great." Only realized a short while later that I've actually never spoken about any of our ion work, and creating a presentation from scratch. It's been a while since I've done this, so I have to thank particularly Concho, one of my graduate students, for helping out with many figures and so on. But it was good, and in retrospect, I'm glad to have this presentation. This is a growing portion of the work that our lab is doing. I'm going to give you kind of two parts to this talk. I'm going to present the general problem which we're interested in, some of our initial results. Again, we've only been doing this for about 2 years or so. But the results that I present almost more of a tutorial or background and more details on the methods. We're going to talk more about some of the computational methodology that we use, kind of, and how that applies in these specific cases, and hopefully that'll put a lot of the work that you see published out there on ion channel dynamics and computational methods in general, put some of that in context for you so you can hopefully understand the basis of it and what you want to believe, what you don't believe, and so on. First of all, I actually need to thank Jamin Sweet, who was instrumental in getting us involved in this work, perhaps due to proximity that his offices too are down from mine, but even before they moved here, we kind of connected, we met up at my physical society, talked about some of these things, and it seems like this would be a right area to moving at that activation of PK channels as a practical method. A lot of whenever I show any experimental work, any of this wonderful physiology work, this basically is coming from Jamin's lab, and I have absolutely nothing to do with it. It might not all be kind of attributed to them, or at least to Gayatri, a former graduate student who was in this lab, but it should be taken as so. So we're going to be focusing primarily on a class of potassium channels known as BK channels. These are BK channels, comes from the name. These are big potassium channels, large conductance potassium channels. They have a unique structure, like all potassium channels. They've got these central 6 helices, essentially, but they have this extra S0 helix. But they still functionally have the same core, the same kind of voltage sensing region, and so on. The cytosolic part is perhaps a bit less defined. We're pretty confident. We know that we've got certainly an RCK1 domain on the cytoplasmic side. There is a putative RCK2 region that may or may not be there. We have things further down the C-terminal regions, such as the calcium bowl and so on. But what makes these channels most unique and most interesting for us to study, and again, when I say us, I'm talking about the large us, the SWE lab and my lab, that they're gated not only by voltage, but also by volume of calcium, and intracellular calcium and intracellular magnesium. The activation pathways for these 3 different processes are separate. And obviously, they result in the end and in the final opening of the channel, so they have to kind of join at one point. But the voltage action activation appears to be largely due to the traditional voltage sensors, S2, 3, and 4, in the membrane spanning region. Calcium activation, as we're going to talk a lot about today, involves primarily the cytoplasmic region, as far as you can see. And magnesium activation has been shown to involve both a membrane spanning domain as well as the cytoplasm. Calcium activation, I think, is most easily observed, again, through patch plant experiments. We're here at 0 calcium. You see as you increase voltage, you increase the open probability of the channels. Okay? But even at this voltage, which didn't activate or open the channel low calcium, if you increase the calcium, you increase the open probability. And this open probability is again further increased as you increase the voltage. Okay? So we have activation through both voltage and calcium in these experiments. And this is an important role. These channels play many important roles in physiology. One of the key ones, as pointed out a few years ago now, was how these channels function in regulating blood pressure. And so, particularly in smooth muscle cells and lining mesothelium, when you have inward rectified calcium channels, will lead to muscle contraction as calcium flows into the cell. Okay? And calcium, in turn, will result in activation of these BK channels, okay, which will repolarize the membrane. Calcium flows out, okay, and effectively shuts off these inward rectified channels and allows you to relax. This is shown, again, from the same Nature issue. This is the actual paper on vasoregulation through these channels. You see that in the knockout mice, you have increased blood pressure as well as increased heart per body weight. Okay. In addition to this role, in terms of blood pressure, there's an interesting neural component to this. There's a particular form of epilepsy, it's called linked with absence epilepsy and paroxysmal dyskinesia. This here is a young girl who has this combined condition where she undergoes an epileptic seizure, okay, and then later on, when she's actually participating in kind of this dance routine or whatever, and goes through this dystonic phase where you see actually she becomes completely distended, and this is the paroxysmal dyskinesia condition. This was first described in 2000, but then later linked again to a particular mutation in these BKCA channels. Okay? It's a point mutation, basically a missense mutation, where you have a single glycine, or an aspartate that gets turned into a glycine through a single codon swap. Okay? And this, in human channel, this occurs at position D434. Okay? This puts it in the cytoplasmic domain, specifically in this first RCK domain. And you can see that in human cow, as well as all these other species, this aspartate, in particular this whole region here, is highly conserved. Okay? If we look at this in terms of, again, going back to the electrophysiology, this mutation turns out to be a gain-of-function mutation. It makes the channel more sensitive to calcium. It's not constitutively active, but it has a higher open probability and increased calcium sensitivity. And again, this mutation lies in this RCK1 domain. Okay, so here you see these voltage traces, and then you go from the wild type channel, okay, and this is the wild type channel at 0 calcium, or 0.1 micromolar calcium. Here's the C434G mutant, and it already has a higher open probability, but then you get a larger shift, okay, when you increase the calcium from 0.1 to 2 micromolar. Okay, another parallel piece of evidence actually came from looking at the function of this RCK domain, okay, the cytoplasmic domain, and comparing this between mouse, okay, which is the M-slow, and Drosophila. Okay, at low calcium concentrations, you see that these are the actual traces now, the current passes. As you increase the voltage, the mouse channel activates nicely. The channel from Drosophila, the T-slow channel, activates very little, but as you increase the calcium, now the Drosophila channel activates remarkably fast, okay, so it shows much increased sensitivity to calcium as compared to the mouse channel. But what's of particular interest is if you go back and swap the same N-terminal piece, so we're looking at the same RCK region now, the N-terminal region of the RCK region. If we swap that, so here's wild-type mouse and wild-type Drosophila. Now this is at 0 calcium, and so we're just looking at voltage activation. If we swap that and take the mouse with the Drosophila, you can see it's called the AC region, the N-terminal piece of RCK, we lose this activation. But conversely, if we take the Drosophila channel and make a chimera putting in this mouse AC region, okay, we gain activity here, again, at 0 calcium. Okay, so this seems, again, to implicate this RCK1 region and this N-terminal piece of RCK1 with calcium channels. Now, we're somewhat limited. Again, when we're talking about molecular simulation, our starting point is almost always a crystal structure. And, there's only one McKinnon around, and unfortunately, he's fairly busy doing other things. He hasn't done our channel yet. But this is a homology model that we've produced, at least based on MPHA and KV1.2, as well as some information from KVAP. So we produced a homology model of what this channel looks like. Okay. So again, here's our kind of secondary structure motifs. It's made up of 4 identical subunits. We're only looking at the alpha subunits. Function is obviously also moderated by, or controlled somewhat by additional beta subunits. And we're going to be focusing primarily on this cytosolic domain. Okay? And apart from all of the different functions we can look at, we're going to look at primarily at the pathways associated with calcium-dependent activation. Now, from a series of studies from Jameen's lab as well as other labs, Chris Wingel's lab, and so on, it's been shown that there's at least 2 independent pathways for calcium activation. There's a high-affinity site in this RCK1 domain, as well as a high-affinity site in what the region was known as the calcium pole. Okay, we're going to completely ignore this last thing I'm going to mention about the calcium pole, okay, and we're going to simply be looking at this pathway that comes to the RCK1 domain. If we go back to this channel structure, okay, the N-terminal portion of RCK, again, this kind of gold-colored piece here is the cytoplasmic domain. Okay, we're going to be focusing on this simple, or 80 amino acid stretch known as the AC region. Okay, this is a Rossum fold, or half of a Rossum fold, and it has this conserved DRDD loop. And recall that this human mutation, this epilepsy mutation we saw with the position 434, corresponds to this aspartate. Okay, this is called the DRDD loop because it's from the aspartate to D, arginine, R, aspartate, aspartate. So DRDD is a go around. And this aspartate at this position was the one that was mutated to glycine. That gave us this epilepsy corresponding. D367, so this aspartate on this end, this mutation has been shown to kill calcium sensitivity, at least the contribution coming from the RCK1. And both of these, the mutation as well as the D-slow, M-slow, this is the region that got swapped out between the Drosophila and mouse and the TEPD. All these mutations fall into this region. Okay, so this is going to be our central focus. Now, this is where we're going to step back a bit, and I'm going to introduce you first of all to the methodology and stuff that we're going to be talking about. So my lab functions purely in the dry lab regime. Okay, we use computational methods. We use a wide variety of methods, including molecular dynamics, which I'll talk quite a bit about today, homology modeling, small molecule docking, quantum calculations, and so on. But we work in close consort with experimentalists, this is Raman, who give us details on mutagenesis, perhaps thermodynamic and kinetic data, and so on. And kind of this, I guess I'd like to say it's a symbiotic relationship, certainly a two-way contribution. There's many benefits that we have dealing with these computational approaches. The first is that we don't have to worry about any protein purification at all. Okay? When you start to deal with expression purification, here's something you might find in a typical wet lab, okay, whereas in our lab, we often joke, any of you are Unix professionals, we joke that we purify proteins using grep, which works quite well. It's easy for us to make mutations. Now this system, certainly in a lot of membrane systems and certainly a lot of globular proteins, it's not easy to make mutations in expressing your proteins. In terms of PK channels, we've actually met our match, I think, and then again, the SWE lab can produce mutants and test them almost as fast as we can. But at least it's easy for us, again, since we have absolute control over the structure of the protein, we can go in and make mutations wherever we want. Probably the biggest key is that we get molecular level information, okay? In that we're not looking at a simple trace, okay, or looking at the activation of channels. We can actually track this down, or we have almost in some sense too much information. We know the position at every atom at each point in time, okay? And trying to pull information out of that proves to be one of the bigger challenges. Probably this can be a relatively fast method. Again, it's a convenient way to perhaps screen for mutants, okay, to look for potential interactions and so on. Okay. There's, of course, now, I could give you an entire talk on the disadvantages or caveats associated with computational methods. That would just be my purpose. It's we're going to be looking at molecular dynamics simulating our system. Okay? MD, or molecular dynamics, is a simulation method that is really based on nothing more than solving Newton's equation for motion, F equals ma. Okay? We calculate these forces, the F in that equation, using what's called the molecular mechanics potential. I'm going to go over the basis of that. Okay? And by solving that equation, we effectively get the position of the protein, the position of the atoms, every single atom, water molecule, lipid, whatever in our protein, as a function of time. In developing what's called the molecular mechanics potential, okay, we have to make several assumptions. The first is that we're decomposing, okay, this potential really is supposed to describe the potential energy of the protein in a given configuration. We first suppose that this free energy can be decomposed into two contributions. The first comes from bonded interaction. Okay, so this is where atoms are physically bonded to each other within the structure. The second then is these non-bonded interactions, okay, which have several different contributions from electrostatic interaction. Okay, then we take each of these terms and further decompose. The first bonded term that we deal with is the stretching of a single bond itself. So every time we have two atoms that are covalently bonded, and think about the backbone, about the C alpha C contribution, or the CO in a carboxyl group or something like that, each of these bonds is really properly described by a Morse potential. If you remember back to your basic chemistry that you had in high school. But this describes the stretching of a bond over a long distance, but in fact, in our simulations, we're really looking over relatively small fluctuations around an equilibrium point. Okay? Because that equilibrium point is a minimum, that means that the first term that we would have to describe going around it, to describe fluctuations away from that point, is going to be a quadratic. And there can't be a linear term since the first derivative is zero. So we can use a harmonic spring or a harmonic oscillator, okay, or a Hookean spring, if you will, and we can describe fluctuations around some ideal bond length using this simple quadratic equation. This has several advantages. First, every time I have a configuration, I need to calculate all the forces on my atoms. Okay, I don't want to calculate an exponential and then square it. Okay, to back out all of these complicated interactions. If I can get away with using something as simple as a quadratic, and if I need forces, I don't even need to calculate and differentiate it numerically. I can differentiate right here. We use the same thing for angles. Okay, we've got some ideal angle, theta naught, and we look at fluctuations. Okay, so anytime we've got three atoms in a row, okay, we've got some ideal angle term. Think of a water molecule where you've got fluctuations in the HOH bond under an angle. These energies tend to be slightly less. These are slightly softer. These are about 10 to the minus 2 kcals per mole per each degree. Whereas for a bond, okay, from a single bond to a double bond, they can vary in strength. So these are really the stiffest modes in the system, are these bond fluctuations. And if you get better agreement, okay, if we are willing to pay the computational price of having a more complicated energy functional, if you will, you can actually couple, this very complicated force field that couple an angle term with a bond term. And that if I bring the angle together, I should increase the bond slightly. If I take them apart, I could really decrease the bonds, and the atoms can come close together. But that's far beyond the The third contribution to the bonded part of the potential comes from a torsional term. Okay? So here the easiest is to go back again to your introductory chemistry and remember the conformational states of ethane, where you've got this staggered conformation if you're looking down the CC bond versus the eclipse conformation. Okay? These torsional terms are first of all fairly weak. Maybe these peaks correspond to an energy of 1 to 2 kcals, and they're going to have some periodicity that is best described using a cosine series. Okay, so these terms are small. They don't contribute greatly to the overall dynamics of the system, but they're important for getting the equilibrium structure. Okay, so that's the last of the bonded terms. The non-bonded interactions, we deal with two primary contributions. The first comes from electrostatics. Okay? Charges on these proteins, on the biomolecule, are not evenly distributed. We already know that we've got acidic groups, basic groups, we've got aspartate and glutamate, as well as things like lysine and arginine. Okay? But even if you look at the atomic level, for a neutral amino acid, for something like glutamine, okay, the charge is not going to be evenly distributed throughout the molecule. And there's methods that have been developed to assign what are called partial atomic charges. So to get something that's neutral, I'm going to have partial atomic charges on all of the various atoms. And when I sum them all up, say for a neutral residue, I'll get to 0. If I sum them up for an acidic group, I'll get to -1 and so on. Once we do that, they're going to use nothing more than Coulomb's law to describe the electrostatic interaction between all these atoms. Okay, so plus attracts minus, minus repels minus, the like charges repel, opposite charges attract. Okay, so nothing more than Coulomb's law. Likewise, van der Waals potentials, okay, van der Waals interactions to capture dispersive forces as well as Pauli exclusion forces, we use nothing more than a Leonard-Jones, this familiar 12-6 potential. Okay, so we've got this dispersive term as well as a hardcore term, okay, to give us the repulsive part. Okay. You put all these terms together, and you have effectively a complete electrostatic potential, a bond term, an angle term, a torsion term, those three bonded terms we talked about. Then we've got electrostatics, okay, and van der Waals interaction. Okay. This potential, okay, first of all, now we've got this potential with all these different terms. Now we actually have to parametrize everything. All of these spring constants, right? Each one of these L naughts or theta naughts or these K values, for example, so it's going to be different depending on the specific pairs of atoms, the specific bond we're looking at. So we have a lot of work to do that, to parameterize this, but through a lot of quantum calculations, looking at crystal structures, using things like Raman Spectroscopy, which can give you ideas, measurements of bond fluctuations, you can actually do a very good job in parameterizing. And I would actually go as far as to equate this more to an experimental method. Okay, using this type of potential to simulate the dynamics of a protein probably more closely correlates to an experiment than to some kind of theoretical construction that I've come up with. Okay, there's a lot of debate there, but more philosophical question. But there's lots of these, we don't parameterize these things themselves. We use one of these existing force fields. We've heard of Amber, Charm, OPLS, Amoeba, developed here at the medical school by Jay Connor's group, and so on. And there's several standard force fields. So we needed forces, but I just told you how we parameterize energy. Okay, but what we do is once we have the energy on this potential U, okay, which I called E in the previous slide, just confuse you. Now I'm having minus the negative gradient of this potential is going to give me a force. Okay, so here's my potential surface U, right? The gradient, the slope points up. Okay, so when I take a negative gradient, it's going to force my particle in this direction. Okay, so things are always going to effectively run downhill to the minimum. we've got these forces. Now we know the masses of each of our atoms. That gives us the acceleration, or effectively the second derivative of position. Okay? So now we've got coupled differential equations for each atom. We have to solve this in this huge coupled sense, but I can write down the differential equation for each atom of my equation. And we're obviously going to solve these numerically, right? There's no equivalence to the hydrogen atom in molecular dynamics. Now, to solve this, we have to go through two separate things. Since we have a second order differential equation, we need, first of all, the position, okay, the zero derivative, and the velocity, the first derivative, in order to solve the second order differential. Okay? We have to look at the initial conditions. Conditions, okay, we start with our protein, ideally a crystal structure or something like that, but now we need to add in, first of all, the rest of the environment. We want to look at the interaction of this protein with potentially water, lipids, if we're looking at a membrane, ions, maybe some other cofactors, maybe more than one protein there. So we add in the solvent, or what's often called solvent, but the water molecules. If we want to embed this in a membrane, we have to consider the type of lipid that we're putting this in. Okay? Salt ions, usually we just add monovalent stuff. We set the pH, so we've got ionizable groups, okay, that might have variable pKa's. We set the pH in our simulation, and then we're ready to go. Our crystal structure, or perhaps a homology model or something along those lines, is going to form the starting set of coordinates. But we can't use it as it is. We have to, first of all, minimize it. We want to minimize its potential, get it down so that each of these, hopefully, ideally, each atom is in its minimum position. We'll get rid of strained bonds, angles, potentially overlapping atoms, which have van der Waals, steric clashes, and so on. Okay, so we minimize it until we get down to a minimum of least close enough. Okay, that's the zeroth derivative. That's the position part. The velocities, we make use of very simple axioms from physics, mainly the equipartition theorem, that tells us that each degree of freedom in our system, okay, is going to have kT over 2 of energy. So kT, this is Boltzmann constant times the temperature. Okay, this is the thermal energy that you've got, which is driving the system. Obviously, if we were to simulate a system, all those simulated systems at 0 degrees Kelvin, where there's no motion, but when we're performing this at 300 Kelvin, or room temperature, we've got this thermal energy which is really driving the dynamics of the system. Okay, so this means that the average energy for a given mode, a given system, is going to be the sum of the square velocities, okay, times the masses for all of the atoms in our system. Okay, so we've got this amount of thermal energy in there. But how we partition that, okay, actually comes from choosing random velocities from what's called the Maxwell-Boltzmann. So based on that equipartition theorem, you can actually develop a probability distribution for velocities, okay, which would look something like this. And once we set the temperature, okay, then this entire distribution is set, and then for a given mass, for a given atom, we'll simply choose a velocity randomly from this distribution, and we've got enough atoms in the system that the averaging will work out over the distribution, so we'll get the correct temperature to start with. We want to equilibrate. Our minimized system should theoretically correspond to a temperature of 0 degrees Kelvin, okay, where things are sitting at their absolute minimum. But we want to simulate something, let's say, at room temperature, about 300 Kelvin or so on. Okay? So we need to apply heat. But this is an equilibrium simulation method. Okay? And so I can't simply crank up the heat, otherwise my system is going to be far from equilibrium, and I'm not going to trust the dynamics of getting from my minimized point to my equilibrium point. So I heat slowly, okay, perhaps continuously by raising the temperature, or heat small, say 50 Kelvin steps, to take my system up to temperature. Okay? And I do that slow enough. The temperature coupling actually comes through coupling the system to a heat bath. And again, this is where we make direct connection with the experimental situations. You can imagine if we're doing a Helmholtz system or a constant volume, say in temperature, we have an NBC ensemble. More likely, we're dealing with someone doing an experiment in an open test tube in a lab or something like that with a constant pressure ensemble. And then we scale the pressure and the temperature. And this very closely mimics the experimental situation. Okay. Finally, and this is perhaps the most humbling part, is that we go through all of this But based on these potentials, remember I said that these bonds, covalent bonds, are really the stiffest part of the system. And because the potential describing those is so stiff, we have to take 1 to 2 femtosecond time steps. Okay? This is 10 to the minus 15. This is a ridiculously small time step that we have to take. And we want to get up simulations that are going to be on the order of nanoseconds, potentially microseconds. We're talking at least 6, 7, 8, 9 orders of magnitude higher. Okay? The amount of work that goes through for a system scales somewhere between the number of atoms n, so it scales between n log n versus n squared, but we want to pay close attention to the size of the system to get the fastest throughput we can. Okay? But we need to simulate and equilibrate this for about 20 picoseconds, and then after that, hopefully we can perform what's called production run, where we can just start to collect our data. Okay? And in the end, if you do everything correctly, hopefully you end up with something which might look like this. Okay? Here's our water molecules. This isn't my simulation, but somebody put it on the web, actually, not acknowledging them, which is good that they are. Here's our ion channel here in blue. We've got our lipids. Here's the head groups, and these greasy alkane tails. And here's all of our water molecules. So oxygen is red, hydrogens are white, and so on. And you've got this time course of simulation, which might be tens, hundreds of nanoseconds. Now, in simulating our system, we're going to make a pretty hefty approximation at this point. Okay? That channel I just showed you, very nice. Right? We've got the lipids, we've got the water, we've got ions, we've got everything we want. Okay? But it would mean that I would never get an answer before successive grand tools. So what we're instead doing is we ignore the full channel, okay, and we just focus on the AC region. This is the key part which is picked out in a couple of the chimeras, okay, and the epilepsy mutation, and so on. And we're just going to focus on the dynamics of the AC region. Now, I would argue that this is reasonable since this AC region is largely a self-contained domain. Right? It's cytosolic, so if I simulate it in water, I don't have to worry about a lipid environment, so there's no key interactions there. Okay? But we are making this approximation. And in this sense, I think hopefully I can convince you that the ends justifies the means, but I need to point this out. Said we don't have a crystal structure. Luckily, we have a bacterial structure, though, for MPHA. In MPHA, we have this result, this cytosolic domain, okay? And if we do an alignment between mouse region, I've got the soft link here with this MPHK RCK1 domain, you see that the alignment is actually pretty good. Okay? There's one point where we have this insert, which interestingly is actually this DRDD loop itself. Here's the DRDD in the mouse channel up top. Okay? But we have, again, well-defined methods of rebuilding this loop in. The bacterial channel just kind of cuts off and cuts this loop off here. Okay, so here's our AC domain, and we've got the secondary structures labeled here. We've got beta A, alpha A, through the DRDD loop, beta B, alpha B, and then through beta C and alpha C. Okay, so we've got this alternating cross control structure. Okay, we go through, we take care of all the details which I told you about, and we perform these simulations for both the mouse channel for M slow as well as the Drosophila channel. These are our first point of comparison. These are the actual trajectories that you get. Okay? They're very pretty. Now the challenge. Yeah, keep going.
But probably a secret end.
So the ends, so this goes along with the approximation. The N-terminal ends, I wouldn't worry too much about because that's in this kind of this flexible linker that goes up to the cytoplasmic domain. This is the first piece after you come out of the membrane. RCKA is the first domain you get. The C-terminal end, we've cut it off, and it's flopping around there. I should add that to my list of caveats in the previous slides.
Also along the same lines, you still assume that the core is easy and demonstrating.
True.
Yeah. And if that assumes that means that the system is conservative. Changing energy with other parts of the molecule, but by itself is not conservative.
True, yeah. That's
So that any kind of idea of how much energy is changed.
Yeah, it's, and that's a point that it's a question.
Well, it's more concerned around open systems and then question your industry is a different service.
Right. You can imagine people have actually done, there's many labs that have made, they're living doing this. This is, like I said, this is new ground for us, but there's been beautiful simulations, even for applying external stimuli, applying electric field to try and activate the voltage sensors or such things, basically applying chemical gradients, to look at throughput through channels or through aquaforms, applying pressure. So there's been lots of simulations done like that. Here we're assuming we've taken this reductionist point of view, we've cut out this AC region, but we're looking at the dynamics of it by itself.
Is it the gas dynamics for the water?
Yeah, so this is in full water at 300 Kelvin. I think the ionic strength, I don't know, I did these a long time ago, but I think the ionic strength in this case is 50 millimolar. So it gets down to the point though now, okay? This is a simplified view in that I'm only showing you kind of the backbone trace of these atoms, right? You can see the alpha helices, the beta sheets, and so on. But now what do we do? How do we compare the dynamics, the differential dynamics between these two channels? And the best method that we came up with was to calculate what are called root mean square fluctuations. Okay? So it's intrinsically difficult to compare dynamics. In this system here, we've got, I don't know, perhaps around 6,000 to 10,000 atoms. That's probably closer to 10,000, 15,000. That means we've got roughly 30 to 45,000 degrees of freedom, okay, of just spatial movement. But we want to choose relatively simple measures, and this RMSF measure, okay, is kind of what we found to give us the best measure of all. So it's root mean square fluctuations is what RMSF stands for. It looks exactly like a standard deviation. And then I go from these trajectories here. Over the course of the trajectory, I calculate an average position. Okay? I pit the proteins to each other, calculate an average position. Then I look at how much, I'm just looking at C alpha, how much each residue, or each C alpha, fluctuates around its average position. Okay? If it doesn't fluctuate very much around its average position, if it's stiff, if it's strained, and a secondary structural element, I get a small value of RMSF. If I'm in a flexible part of the protein, where I get a lot of fluctuations around this mean, and then I have a large RMSF. Okay, so it looks a lot like, if you're familiar with crystallography, like a temperature factor or a beta factor from NMR or something. Okay, so we go back and we look at these simulations we had, and here's the average, or the extrema for the M flow as well as the D flow structure. Okay, and what we see is that alpha B, okay, this region here, exhibits a significant change in the dynamics. In that in M slope, you can see the green curve, okay? This region of alpha B, this N-terminal portion here, is quite dynamic, whereas in D slope, it remains rigid. Okay? And then you can see, so we're gonna correlate this later to more of the function. This was done I think 3 years ago now, 2-3 years ago we published this work. Okay? And I don't think we fully understood the implications of this work in the sense that we picked out this one region, and we basically showed that, well, we've got these AC regions, which is this exhibit dynamics. This decrease in dynamics of alpha B correlates with first of all, increased calcium sensitivity, those D-flow traces that I showed you before. Okay. But interestingly, there was no observable difference in the dynamics of these DRDD loops where this calcium is close to 65. Okay, you go back and take a look at these. Here's the DRDD loop here, this peak here. And we see that really no change in the dynamics of these loops at all. Okay, so now we change gears and go back to look at this epilepsy, what we would call the epilepsy mutation and the GEPD mutation in calcium. So mutations, if you go to the mouse channel, we talked before, said this is isolated in humans at position D434. This corresponds to D369 in the mouse channel. Okay, so that's, I'm going to be talking a lot about D369, but this is the same GEPD mutation that was isolated before. experiments showed that this glycine mutation, which was again the hallmark of this GPD condition, increases the calcium sensitivity. So now we're looking at the V1 half for channel opening as a function of calcium concentration. So the wild type channel is this thick black line here. It's a series of alanine, glutamate, asparagine, proline, tryptophan traces shown on here, which don't differ significantly from the wild type. But the glycine mutation shows an increase in calcium sensitivity. Okay, so it opens at a lower voltage for the same calcium concentration. What's interesting, though, is that things such as alanine and proline don't show this effect. So now to test this in this case, we actually went and created 4 separate models. We have now the wild type M flow, which we've already simulated. And now we create mutants, 2 control mutants, to do an alanine and proline mutation at the same point in the DRDD loop. And then we create the GPD mutation, this glycine mutation. Okay. We're going to simulate all of 4 of these channels. Okay. We're going to do them for about 80 nanoseconds. And we're going to compare their dynamics or the RMSF analysis that we did before. Okay, so when we do the RMSF, this is what we get. So the wild type is this white curve flowing through here. We've got the alanine, we've got the, I guess they're alphabetical order, but the alanine and the proline are the red and blue curves. As you can see, they basically track the wild type RMSF values before. But the glycine mutation, shown here in green, okay, it agrees, even over the DRDD loop, and the same motif here, we're making the mutation, but it differs in the region of alpha B, as well as in this beta A, alpha A linker on the other part of the protein. And so the wild type, same curve again here, the wild type alanine and proline mutations essentially show identical dynamics in terms of this RMSF, but this glycine mutation and this GPD mutation exhibited different dynamics, and not at the region where we're making this mutation, okay? But actually, again, back in the same region, in alpha B as well as in this beta A alpha A link. To exemplify this a bit more, put this back in the structure. Here's this aspartate here. This is where we're breaking this mutation. We're putting glycine in here. Okay, it's an unstructured surface. Structural biochemistry, and you would think that, you're putting a glycine in here, it's already a sloppy loop out there in solution. It's not going to have any effect at all. Likewise, putting a proline here, you'd think it would make it more rigid, and alanine might be kind of a null or, again, a control mutation. And indeed, all of those substitutions, apart from the glycine, show no change in dynamics. But the glycine mutation at this point, again, shows a change here at the distal part, and this is the opposite end of the protein, at this beta A alpha A linker, as well as in alpha B. So this is a classic allosteric effect. It's perhaps a different version of allosteric than what you read about in one of your standard biochemistry books. So it's not kind of the standard bind and introduce a conformational change. Okay? And then the average structures that we see coming out of these simulations are essentially identical. What is different is how much they fluctuate around those average structures. Okay? So this is a classic version of allosteric is known as kind of a redistribution of an ensemble of dynamics, okay, which was really first described back in 1984. Okay, so we're making this mutation up here. Again, this is the point where calcium is binding, and we're seeing a change in dynamics at the bottom of the loop. So we want to investigate this in a bit more detail. Okay. So developed the method, we didn't develop the method, we simply applied this method where we start with an initial structure. We've got the same starting coordinates. But we simply choose different sets of starting velocities. Okay? So we choose different seeds for the random number generator. Remember, I said we're choosing from this probability distribution. We assign different velocities, and we start 10 separate simulations, which all head off in different directions. They're correlated because they all start from an initial the same starting point. We can calculate basically what the correlation time is, and after about 1 or 2 nanoseconds, they effectively are at independent points in phase space, and we simply let all of these 10 simulations run, okay, in this case for 50 nanoseconds, so we get a total of a half microsecond now of simulation. Okay, so this is a couple orders of magnitude more than what we had before. Our analysis method also became slightly more fancy, let's say. Okay, so to get some measure of statistical significance, what we can do is calculate this autocorrelation time, again, within the structure. We find it's about on the order of a nanosecond. Okay? That tells us that for each nanosecond we get effectively an independent structure along this trajectory. These numbers, actually, I realize that come from different. So we get about 50 independent points for each trajectory. We sample these roughly 100 times. Okay? Then we can actually apply statistics. So we get a single point, we get a mean value for this RMSF as well as the standard error of the mean, which allows us to apply statistics such as the student t-test, okay, to look for significant deviations from the dynamic. So when we do that, this is a very colorful plot now, but now the wild type, okay, we've got a curve with some width to it, is this magenta colored spot. Lysine is in yellow, okay, and the regions where they overlap comes out as cyan. And the region, again, you can pick out as being significant is this same piece here, okay, where the cyan essentially goes to 0. So we can apply, again, a t-test at a confidence interval of maybe 0.05, and we say that, okay, we see a significant change in dynamics for the same region of alpha B that, again, we identified in the D-slow M-slow phase as well as what we saw in the individual simulation. Okay, so this seems to be one of the key. Form a couple more methods of analysis, hopefully to give us a bit more insight into how this functions. Okay, one of these methods is normal mode analysis. So systems such as ours, in this case, seldom have single degrees of freedom. Okay? And because of that, these motions are coupled, okay, between all these various degrees of freedom. It becomes difficult to kind of pull out the essential motion. If we just look at it, here's a simple system of two masses, okay, a one-dimensional plane here, being driven, say, by some external force or by thermal energy, whatever you want to think about. And there's only 2 degrees of freedom, right? I can describe this uniquely by the length of each of those 2 springs. But if I look at the dynamics, okay, the dynamics is essentially very complicated. And if I perform normal mode analysis on this system, I come out with kind of a short, out-of-phase motion with 2 masses moving in opposite modes, as well as an in-phase, larger amplitude, slower motion where they move in phase. If I were to take these 2 plots and add them together, okay, I would exactly recover this complicated dynamic that we have back here. So we do exactly that same thing in this case. And now what I'm plotting is just the first mode. I'm looking at the extrema of the first normal mode for each of these simulations. We see it in the wild type. Okay, we see a fairly large degree of motion. Alpha B here moves to a very large extent. And it's almost like the 2 halves of the molecule are communicating with each other through this DRDD loop. And it's kind of, we're very, take a lot of liberties in kind of interpreting these types of motions. But it looks like through this kind of half of this rock and fold, you've got the 2 parts of the molecule moving, and that this alpha B shows a large degree of movement compared to glycine here. And you see that largely we've got the same degree of motion in this loop. Remember that the DRDD loop showed exactly the same range of dynamics. But now, if you look at this, it's almost like the rest of this motif is kind of cemented together. It's become much more rigid. It sort of exhibits less dynamics than the wild type, which is exactly what we saw in the RMSF analysis. So we can do this in a higher number of dimensions. Here again, this is the first eigenvector and the second eigenvector in this PCA, or this normal mode analysis. Here's the wild type protein. We see it has a fairly large range of motion. And the mutant, okay, here's this 2D projection, occupies a much smaller region of conformational space. So it seems to be much more restricted. Okay. So now we want to go back and try to make some sense of this in terms of experimental and structural results. So remember, we said that this glycine mutation, in terms of the electrophysiology, was somewhat unique in terms of its behavior. And we saw exactly the same thing. We saw that the glycine mutant exhibited this change in dynamics, okay, these 2 regions of the protein. And this region that we identified, it was exactly the same region that we picked up before looking at the SOFLA channel. And if you remember those RMSF plots for the SOFLA, its RMSF values were also lower than the most values, and that seems to correlate with the increase in calcium sensitivity. To figure out what this potentially might mean, and we analyze this in terms of our homology model. So now I'm just showing the 4 regions, so S6 here in blue and S5 in green. Okay, here's the selectivity filter. And then here's just the AC region as part of our cytosolic domain. So this comes directly from our homology model. Here's our DRDD loop, and this is where calcium would be binding, okay, to affect opening of the channel. This is also where we see our epilepsy mutation. But here's this alpha B. So this is the point where we saw this change in dynamics on this region. Okay? All the caveats that we associated, we looked at this protein by itself, absent the rest of the channel. Okay? But it's very interesting now that essentially calcium binding out here with this epilepsy mutation would cause a change in dynamics in this end of the protein that would affect opening of the gate. So simply proximity to the core, proximity to F6, seems very indicative that we're on the right track. There's actually been further mutagenesis work done now in Jameen's lab that has found specific mutations in alpha B that appear to be linking, if we will, to F6 to this region of the core. And these mutations don't give additive effects in terms of calcium sensitivity, in that they seem to be directly associated with the same pathway of calcium bonding and/or this epilepsy mutation. Okay, so everything seems to point to the fact that the alpha B is somehow linked in this activation. And this change in dynamics that we see, you know, we equate this shifting somehow to almost like a spring. And that if you can imagine binding calcium on this side, I want to affect the conformational change of calcium binding to some structural or dynamical change in the other end of the protein. Okay. If this region is stiffer, it's more efficient in transmitting the binding event here to a dynamical or structural change on this side. Okay, so we would correlate this decrease in dynamics with this increase in calcium. Okay, so just to kind of wrap up some of the ideas, this AC region we see as really central to a lot of the calcium sensitivity, again, ignoring the calcium bowl, but that's my centric worldview. And this decrease in dynamics or flexibility in the AC region appears to correlate very strongly with increases in calcium sensitivity. In particular, the dynamics of alpha B, this alpha helix at that bottom, quote-unquote, is one of the key structural elements, and it looks like it makes direct connections now with this transmembrane helix, S6 to the 4. And we've got a lot of work ongoing for various aspects of this, looking at different mutants, trying to characterize them, as well as looking at the actual means of calcium binding. Right? If you've been paying attention, you notice that we're talking a lot about calcium sensitivity, whereas calcium has not entered any of our simulations yet, just because we don't know enough about the coordinating sites where it bonds, but we're trying to solve that problem. And of course, I had, like I said, I've never talked about this work, and most of the work has actually been done by the graduate student at Conscious Center. Waylon Cheng is another NSCP student who's working together between my group and Colin Nichols' group. He's actually even more brave. He's actually doing both the experimental and the computational side of things, working on KIR channels in this case. And then obviously Jeremy Sweeney, Gayatri, and other people in the SWE lab. Thank you for your attention. Take any questions?
Did you calculate any experimentally observable data? I mean, because all this normal modes or fluctuations are not observable. I mean, it's possible to experiment independently actually measure.
True. I agree. It's not clear what we could calculate. It's a lot of correlative phenotypes that we observe right now. If we could at some point, so let's imagine that we get some new computers and they allow us to scale up, and we can implement all of this in a channel structure. That would give us a lot more insight. We can, I guess, maybe I'm selling myself a bit short. We have picked up perhaps particularly mutations as well as this pathway. When we go back, so as I said before, Jameen's lab, they can produce mutants overnight and test them. They've done a complete alanine scan of the whole AC region. and it picked out a series of residues that give significant changes, more than kind of sort of a 2 sigma effect in terms of calcium sensitivity. And they seem to derive a pathway, if you will. And that pathway does, in a certain sense, correspond with changes in dynamics. If we look at correlations between hydrogen bonds or correlated movements within the structure, it kind of picks up the same pathway through the AC region.
No,
Likewise with so you know, in terms of electrophysiology, you know, we're far away from that. But in terms of mutagenesis and predicting what effect mutants might have in terms of dynamics, you know, that's the only, right now, that's kind of the only other level we're looking at.
no, what I mean is in molecular biology, what people actually measure is a binding constant or binding energy. And it's not clear how this normal mode fluctuations are related to the binding energy.
So I wouldn't say the normal modes are all connected. We're looking at the dynamics there. Once let's optimistically say we can identify this calcium binding site, then we could actually make a change. So all of this analysis, all the electrophysiology results, you could interpret in terms of a standard concerted MWC type model and come up with apparent affinities as well as activation energies of the channel. And you could correlate perhaps those binding affinities with ones that we can measure in our simulations with mutations. That would be one potential.
The apparent rigidity of the ERGD all cause of the increased flexibility imparted by glycogen.
So, yeah, no, good point. And, you know, that's certainly what we would have assumed at first pass. It seems like if you go back and look more closely at the dynamics, it seems like the loop has a certain amount of dynamics, first of all, or almost communication between the two ends of the protein. And with the glycine mutation, it shows the same level of fluctuations, but the orientation or the direction, if you will, of the dynamic is different. So it does tend to kind of flap more, and almost like it removes this communication. So it is functioning somewhat like you would think. You don't see it in the RMSF plot because there's already intrinsic dynamics in this loop, but it's kind of hidden.
You were talking about 4 subunits, and the ones we're looking at here, I guess those are individual units. And if the 4 subunits are arranged like in a ring in the membrane, if you look at it the other way, it tends to see a hole in the center, right?
Right. I don't have any of those pictures, but yeah, absolutely.
Structures like beta barrels and things that empty.
Sure.
When you look at the structure from the other way, you actually see a hole in the structure. And then when you bind, just that one of the 4 units is going to go asymmetric, which has a smaller hole. If you bind it all 4, it's symmetric. So you can either have a larger or a small opening in the structure to make the channel. It's more of a comment, but
okay. Yeah, no, that's absolutely true. I think, you know, I guess we dream someday of being able to get up to that level of detail. You know, this is a level that you could never hope to get to in an experimental situation where we can actually have a channel and activate one of the subunits by binding calcium. Look at the intrinsic changes that it does. You know, look for this asymmetry and then kind of work your way through adding calcium, activating one domain at a time.
well, you know, some of the motors they've looked at the ATP binding. It tends to be random. It's like a five-fold channel with random binding for process mediation.
Right.
Any other questions or comments to David? Thank you for a great talk.